In this video, we shall look at a few problems associated with conservation of energy with friction factored in. Problem 1. In figure below, a mass 2 kg, so that is this mass right there, is released from rest at point C on a track that is 1/4 of a circle with radius 1.5 meters, so that R is 1.5 meters. It slides down the track and reaches point D. So it slides down like that and gets to point D with speed 4 meters per second. So at point D, it's moving with a speed of 4 meters per second. From D to E, it slides a distance 3 meters. So that distance is 3 meters. And then comes to rest at point E. So at point E, the speed is 0 meters per second. Find the coefficient of kinetic friction on the horizontal surface. So let's do that first. So part A. Point D is your initial point and point E is your final point. I'm going to take the horizontal level as the 0 level for gravitational potential energy. Like that. So let's write down conservation of energy for this problem, relating the initial point to the final point. What are the forms of energy? The first is, of course, the gravitational potential energy. So at the initial point, plus the kinetic energy at the initial point, and then you also have work done on this object by friction as it moves from D to E. Note, that is the direction of displacement to the right. Friction always opposes motion, so that is the direction of friction. So let's write that work for now as WF. At the final point, of course, there is kinetic energy term. And then there is this gravitational potential energy term, UFG. And they must balance out. That is what conservation of energy is all about. However, we note that UIG is 0. UFG is 0 because both the initial and the final points are at 0 joule level. Also, the object comes to a complete rest at point E, namely at the final point. So that goes to 0 as well. Another thing to note is the work done by that friction on the object as it moves is a negative work, and it's given by minus mu sub k times normal force, so that is the kinetic friction, times the displacement. In this case, it's 3 meters. Now, why is it negative? Because friction is to the left, displacement is to the right. Now, note that the normal force is quite simply the weight, because that is the weight, 2 times gravity, and the normal force equals the weight in this case. Putting everything together, the kinetic energy at the initial point is half times mass, which is 2 kg. The speed is 4 meters per second, so 4 squared. Note, the work is a negative work, minus mu sub k, we don't know. Normal force is the weight, which is 2 times gravity. And the displacement from D to E is 3 meters, and that equals to 0. And you see that you can solve for the coefficient of kinetic friction. Solving for mu sub k, you will get 0.272 for the coefficient of kinetic friction. Now let's do part B. How much work is done on the mass by friction as it slides down the circular arc from C to D? So in part B, point C is the initial point and point D is the final point. So let's write down all the energy. The gravitational potential energy at the initial point plus the kinetic energy at the initial point. Remember now, again, there is this work done by friction as the object goes from here to here. So that work needs to be factored in this manner. And that equals whatever amount of energy it has at the final point. So the gravitational potential energy at the final point plus the kinetic energy at the final point. I'm going to take the horizontal level as before to be the 0 joule level for gravitational potential energy. So the gravitational potential energy of this object at the initial point is the mass times gravity times this length right there, which is just the radius of that arc, and we know it's given by 1.5 meters. 1.5. The kinetic energy is 0 because it is dropping from rest. The work is a negative work, but since we are solving that, let us just keep that as the variable to be solved, equals the gravitational potential energy at point F is quite simply 0 because of our choice for U. The kinetic energy is half times the mass times the square of that speed. And you can solve for the work due to that friction, which will be minus 13.4 joules. And that solves the problem. Problem 2. A 4 kg box, so this is a 4 kg box, is pulled 5 meters. So from here to there, let's say, the distance is 5 meters along a horizontal floor at constant speed. So that means the acceleration is 0 meter per second. The force exerted is 8 newtons, so that is the force, at 12 degrees above horizontal, so that is the angle. Find the work done by the force. That is simple. That is quite simply the force dotted into displacement. So in this case, it is quite simply the magnitude of force times the displacement times cosine of the angle in between. In this case, is 12 degrees. So the force is 8 newtons. Displacement is 5 times cosine 12. And that's going to give you 39.1 joules. Part B. What is the work done by the friction? Now we know that friction opposes motion, so that is the direction of that friction. Kinetic friction, that is. The object is moving with 0 acceleration because we know it's moving at constant speed. So friction must be the same in magnitude as the horizontal component of that 8 Newton force, which is 8 cosine of 12 degrees. So the work done by friction is friction force dotted into displacement. If we take the rightward direction to be I hat, the leftward direction must be minus I hat. So the friction is given by minus 8 cosine 12 degrees I hat, and you dot that with displacement, which is 5 I hat. And you will get the answer with same magnitude as in part A, but with opposite sign, minus 39.1 joules. Part C. Let's determine the coefficient of kinetic friction between the floor and the box. Now note that this box is subjected to few forces, and these forces are, the first thing is the weight, which is 4 times gravity. You have a normal force, like that, and then you have this kinetic friction, F sub k, and you have this 8 Newton force acting at some angle, namely 12 degrees, and the acceleration is 0. From the definition of kinetic friction, it's given by coefficient of kinetic friction times the normal force. And we mentioned, since the acceleration is 0 meter per second squared, the magnitude of that friction force must be the same as the x component of that 8 Newton force, so namely 8 cosine 12 degrees. So that means now we have to determine the normal force. The normal force is contributed by two factors. One is the weight, and the other one is the vertical component of that 8 Newton force. So that means the normal force is a weight minus that y component of that 8 Newton force, which in this case is 8 sine 12 degrees. Putting this information there and that information here, we can solve for the coefficient of kinetic friction, which will give you 0.208 for the coefficient of kinetic friction. And that solves the problem. Problem 3. A block with mass 2 kg so that's this block, is placed against a compressed spring in yellow on an inclined plane as shown. When the spring is released at A, so that's point A, it projects the block up like that, the incline. At certain point B, a distance 5 meters away from point A, the block's velocity is 4 meters per second, up the incline. If the coefficient of kinetic friction is 0.3 between the block and the surface of that incline, find the amount of potential energy that was initially stored in the spring. So I'm going to denote my point A as the initial point and point B as my final point. And let's apply the conservation of energy here. Now at the initial point, what are the energies that contribute? The first is, of course, the initial energy of that spring that is contained in that spring, the potential energy. And then you have this kinetic energy at the initial location, and you also have the gravitational potential energy at point A. In addition to that, we know there is friction opposing the motion like that, so that means there must be work done by this friction, and that must be taken into account. On the left-hand side, let's call it W sub f. At the final point, when the object is at point B, so you can write the final potential energy of the spring, the kinetic energy at the final point, the final gravitational potential energy, and that's pretty much it. And because of conservation of energy, this sum must be the same as that sum. So let's write down term by term. Let's first look at that term. That is what you want to determine. That is the amount of potential energy that was initially stored in the spring, which is what you want to solve. What about this term? That is the initial kinetic energy of the object. The object is not moving. It does not have any speed at that point, so that goes away. It's 0. Term 3, the gravitational potential energy at point A. Now remember, we have the freedom of choosing 0 joules for gravitational potential energy at some point. I'm going to take that level to be the 0 joule level for gravitational potential energy. So that means that goes away as well. Next is work done by friction. Friction acts downwards, the displacement is upward. So that means it's a negative term. The kinetic friction is given by the coefficient of kinetic friction, which is 0.3, times the normal force, which we can calculate. So this is kinetic friction. And the displacement is from here to there, which is 5 meters. Let's quickly calculate the normal force. The normal force on an object resting on an inclined plane is, so if that is the weight, we know weight is 2 times gravity. The normal force is like that. And the normal force must be the same in magnitude as the component of that weight perpendicular to the plane, which we have shown in our previous video to be the weight times cosine of the inclination angle. Putting this in here, we end up with that term. Remember, this is the displacement. Now the term at the final point. The energy stored in the spring at point B, the spring is completely relaxed, so there is no spring potential energy. The kinetic energy is quite simply half times mass, which is 2 kg, times the speed at that point, which is 4 meters per second, and square that. Gravitational potential energy at the final point is quite simply the mass times gravity times that height, which is h, and we know from trigonometry it is simply 5 sine 35 degrees. Note that this is 35 degrees, the angle of inclination, so this is quite simply 5 sine 35. So equating these two sides, or these two sides, we can solve for the remaining unknown, which is the amount of potential energy that was initially stored in the spring. And solving for it, you get 96.4 joules. That solves the problem. Thank you for watching.